In this lecture, we're going to go over proper plotting rules for trendline and look at examples of linear functions. So we're going to look how to create a proper plot of experimental data containing trend lines. We're going to recognize the shape and boundaries of a linear function shown graphically. We're going to recognize when an equation is part of a linear model, and we're going to determine the physical meaning of units of parameters within a linear function. And then we're going to look at linear relationships that behave according to Newton's second law for various engineering disciplines. So we can use these slope and intercept functions in Excel to determine the slope and intercept of a linear function. So the slope function is used to determine the slope of the best fit of a straight line through the data. Two input arguments that you need are the cell range containing the dependent variables and the cell range containing the independent variables, basically your X and Y cell ranges, and they have to be in that order. Similarly, the intercept function finds the y-intercept. It uses the same ranges as the slope functions. The coefficient of determination, which is your r-squared value, can be used using the RSQ function. It uses the same input ranges again, and an r-squared equals 1 is a perfect fit. It means that the fit curve goes through every line. Typically, you want an r-squared value above 0.9. Sometimes it's not possible to achieve that, though. Using the slope and intercept functions, we could calculate the predicted temperatures and plot them for comparison. So this is a case of where we're plotting our experimental data and then putting a trend line on our graph for comparison using our slope and intercept functions. You can also use Excel's built-in trend lines. A trend line is a calculated curve through a data set. It highlights trends in the data. It's an easy way to perform a regression analysis. Excel has linear, exponential, logarithmic power, polynomial, and moving average types. You're going to use a linear, exponential, power a ton. Logarithmic is actually not covered in this course. To add a trend line, you right-click on any data point of your data series that you want, and you can click Add a Trend Line. You can also use our handy Chart Elements button. This is going to open up the Format Trend Lines panel. In the Format Trend Lines panel, you can choose what type of trend line you want, whether it's exponential, linear, polynomial, or power. You also typically want to display the equation on the chart and display the R value on the chart, because this will tell you the equation and how good of a fit that you have. You can also format the appearance of the trend line to give it different colors, line shapes, to make it differentiable from any other information that's on your chart. And you can also format your trend line by clicking on the equation, which will allow you to change the number of decimals and actually the variables within that equation. So here's an example of a linear trend line within Excel. You have your temperature and your time, which is plotted, and then it's going to give us a linear trend line that says our graph is 2.7758 times x plus 296.11 with a fit of 0.98, which is a pretty good fit. So this is the graph. This is the equation that would fit our data, which we can then use for comparison. It gives you the same results as the slope, intercept, and RSQ functions. So what trend lines exist in Excel? Well, you have a linear fit, which is your equation y is equal to mx plus b. That's in the linear form. B is our intercept, k is our slope. So there's no data manipulation required. To do an exponential fit, it has to take the log of all values prior to performing the regression. It tells you your B and B1. We're going to go through power, exponential, and linear fits in detail over the course of this chapter and how to find the slope and the meaning of the values in the linear regression. For example, in linear, your B1 is just your slope m. In logarithmic, B1, there's different equations that occur. So to use Excel's trend lines, you can right-click on existing trend line, select Format Trend Line to open up the Trend Line dialog panel to choose a different type of trend line. For example, I can turn a linear trend line into an exponential trend line. So what are the proper plot rules for trend lines? All axis labels should include the name of the variable, symbol, and units. Both horizontal and vertical grid lines should be present. You want to add minor grid lines based on your overall look. Experimental data, again, is always shown by symbols. Trend lines and symbols for each dataset should include a different line type, symbol, and line color. Legends are needed for more than one set of data. The trend line equation placement should be as close to the trend line as possible. If not, you want to kind of format it to be the same color, use arrows, and make it descriptive of this is what this trend line is looking at. And trend lines equation should contain values that are formatted to be reasonable, and the symbols in the equation should match the horizontal and vertical axes. So by default, Excel is going to make your graph y is equal to something times x. So you have to go in and edit those equations to actually match the variables in your equations. So basically, it's the same rules that apply for proper plotting. Now we're just adding trend lines to them. So here's a graph of a proper plot with trend lines on it, and notice it has all the information that a regular proper plot has. Our data is in symbols that are different colors and different shapes. We have a legend. What we have now are the lines for our trend lines, so both points in the line types are different colors and different styles. The trend line equations are located near the equations and have the appropriate variables in them. They're formatted with a white background to make it easy for readability. Yeah. So let's look at linear models. The first type of model is a linear model. The ordinate y value is a function of the Abisca x value. So the rate of increase or decrease is a constant. It's called the slope. The intercept occurs at x equals 0. Examples include Newton's second law, distance traveled at a constant velocity. So we're working with our y equals mx plus b equation. So we're looking at our linear straight lines. So some examples of linear relationship, we have hydrostatic pressure, which our hydrostatic pressure is equal to our density times our gravity times our depth. So an increase in height or density linearly increases the hydrostatic pressure. So our intercept in this case is 0. If we want to include surface pressure, we would have an increase in height or density, literally increasing the hydrostatic pressure from the initial pressure. So in this case, our intercept is P surface. They all both take the shape of mx plus b. So what are the units of the constant 176 in this example of a graph of potential energy versus height? Well, we have PE is equal to mgh, so our potential energy is equal to our mass times gravity times height. That is our equation for potential energy. If we use our units, potential energy per height is equal to joules per meter, which is equal to a newton per meter. Newton meter per meter, which is equal to a newton. So the units of 176 in this equation have to be in newtons. So we're trying to figure out the physical meaning of the constant. So our theoretical equation again was PE is equal to mg times h. Our trendline equation was PE equals 176 times h. So if we compare the two, the physical meaning of our constant is our mass times gravity. So our mass times gravity is equal to 176. So 176 is also the weight of the object. So what's the mass of the object? Well, we know 176 is equal to the mass times gravity. We're going to do the mass is equal to 176 divided by our standard gravity of 9.8 meters per second. We're going to get that our mass is 18 kilograms. So now we're starting to see how we can use graphical data to determine information about a system. For example, if I have a plot of voltage versus time, I want to know the units on my constant 1.9 R. The governing law is voltage is equal to your current times time divided by your capacitance. So if we plug in all of our units, we're going to get a volt per second. So what's the physical meaning of our constant? If we compare our theoretical equation to our trendline equation, we're going to see that our 1.9 is equal to our current divided by our capacitance. So that's the physical meaning of the constant. And the value, so what is the value of the capacitor? If we have a current of 50 microamps, well, 1.9 is equal to our current divided by our capacitance. So our capacitance is going to be equal to 50 microamps divided by 1.9 volts per second, which gives our capacitance equal to 26.3 microamp seconds per volt, which is the units of capacitance. It's actually, so an amp second is a coulomb per volt is a Faraday. So we get our capacitance in 2.6 microfarads. So what are some relationships of linear systems that we might know? So we have Newton's second law. When a force influences a change to a system parameter, the system opposes a change according to its internal resistance. When you push a boulder, the amount of matter in the boulder opposes the acceleration of the boulder. So we get our, so if we're going to use this relationship of Newton's second law to see how masses, springs, and resistors work. So basically we have when the system is acted upon by a force to change this parameter, it meets this resistance. So we have a physical object, the eternal push or pull, the change in parameters, acceleration, and its resistance is mass. So that gives us our F equals ma for Newton's second law, which is a physical object. If we look at springs, we have springs. We're trying to push or pull them. The parameter that changes the elongation of a spring. The resistance is a spring stiffness, so we get Hooke's law, which is F is equal to Kx. If we look at electrical resistors, we have our voltage, our current, and our electrical resistance. So our voltage is equal to IR. So in mathematical terms, we have Newton's second law, which is our force is equal to our mass times acceleration. For springs, we have our force is equal to our spring stiffness times elongation, so F is equal to Kx. And for Ohm's law, we have voltage is equal to current times resistance, so V is equal to IR. It's more commonly written as IR, not RI. Doesn't matter. So if we look more at Hooke's law, we have our force is equal to our spring constant times X. X is the change in the system, this is the elongation, K is the internal resistance of the spring. Ohm's law for resistor, voltage is the pushing force of electrons in a circuit. I is the change in the system, it's how many electrons are flowing, or it's our current. And R is the internal resistance of the circle in units of ohms. Ohms are equivalent to 1 volt per 1 amp. How do these equations relate to elastic objects and fluids? Well, instead of a physical object, we have elastic objects. Instead of a force, we have a stress, and the parameter that's changing is strain, and the resistance is Young's modulus. For a fluid, we have our shear stress. The parameter that changes is our shear rate, and the resistance is our dynamic viscosity. So in mathematical terms, our F equals ma relationships, our stress is equal to our Young modulus times strain, and for fluids, our shear stress is equal to our viscosity times our shear rate. In elastic materials, sigma is the force acting on the object applied over an area. It's a pressure, it's in the units of pascals. Epsilon is the change in the system, which is the elongation ratio. It doesn't have any units. And Young's modulus is the resistance of the object in a modulus elasticity. To keep the units of the equation balanced, the Young's modulus has units of a Pascal as well. So if we look at fluids, when force is applied to fluids, it acts over an area occupied by the fluid. Instead of poking at it, you can think of like a piston moving in a cylinder. So the shear stress is symbolized by the Greek letter tau. It's similar in terms of pressure. It's a force acting on a unit area, so it is in units of pascals. Velocity changes depending on your location in the pipe. So what we get is Newton's law of viscosity. This is not resistors. It's tau is equal to shear stress times your change in velocity over your change in height. These are just some linear relationships that might occur in the problems that we're going to be solving. So again, tau is your shear stress acting on the fluid. Delta V over delta Y is the change in velocity as a function of your position in the pipe. It has units of 1/seconds. We're going to investigate power models and some typical engineering laws that fit power models and exponential models. And then we're going to discern information from our graphs. And then in chapter 13, we're really going to look at how we model these on trend lines and information from the graphs. There's a difference between dynamic viscosity and kinematic viscosity. Dynamic viscosity is given by the unit mu. It's in units of poise, which is 1 gram per centimeter squared. Commonly centipoise are used. It's a function of temperature. Kinematic viscosity is given the Greek letter nu. It's the ratio of dynamic viscosity to density. It's in the units of Stokes, which is 1 centimeter squared per second. We also have capacitors, so Q is equal to our capacitance times our voltage. Again, 1 farad is 1 coulomb per volt. We have inductors, where your voltage is equal to your inductance times the change in current over your change in time. Is very similar to shear stress in a fluid. It has units of Henry, which is a volt second per amp. So these are just some common linear type systems that might occur when we're making graphs and discerning information from them. Again, we're going to start going over power models and exponential models as well.